Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here. This is Andrew and Renee. Welcome to the Stack series.
Today we are exploring mitochondrial health, aging, and the energy crisis within our cells.
Yeah, and it is really wonderful to be back. Honestly, with the stack of research we have on the desk today, I think we're going to need every bit of mental energy we can muster.
You are not kidding. And I have to be honest, when we started pulling the sources for this exploration, I had this moment of realization.
Oh, yeah, like what?
Well, you know that feeling when you wake up, you've technically had your 8 hours of sleep, you've had your coffee, the sun is shining, and yet you still feel just heavy.
Oh, absolutely.
Like your internal battery is stuck at 15% and the charger is completely broken.
I think everyone knows that exact feeling. And, in the clinic or just in daily life, we usually blame it on the schedule or the kids, the stress of modern life.
Right. Or we just shrug and say, well, I'm getting older. Exactly. We say, I'm just tired. It's a throwaway line. But what the research we are looking at today suggests is that tired isn't just a mood. It isn't just a lack of caffeine.
No, it's not. It's a biological reality happening at a microscopic level. We are talking about the batteries inside our trillions of cells literally losing their ability to hold a charge.
Which is a really profound shift in how we look at health. Because for the longest time, biology class taught us that the mitochondrion is the powerhouse of the cell.
Right. I think that phrase is burned into everyone's brain from high school.
Yeah, and that is true, but it is also a massive oversimplification. If you look at the sources we have today, from the papers on environmental toxins to the latest on NAD plus precursors.
You realize they're not just dumb power plants.
Exactly. They aren't just chugging along in the background. They are the generals on the battlefield. They are the signaling hubs that dictate whether you age healthily or whether you succumb to chronic disease.
And that is the hook that really got me. The idea that aging might not just be the inevitable passage of time, sand slipping through the hourglass, but actually a breakdown in this specific machinery.
Yeah, the sources are practically screaming that aging itself might be classified as a metabolic disease.
We're going to look at how toxins, diet, and even the way we exercise changes these tiny organs. But before we get to the biohacking stuff, the red light therapy, and the supplements, we have to go back to the beginning.
And I mean the very beginning.
Yeah.
The biological origin story.
Yes. The endosymbiotic theory. This completely blew my mind the first time I read about it.
It's wild.
It still feels like science fiction. We need to walk through this properly because this isn't just trivia. This explains everything about why our cells work the way they do today.
It really does. It's the foundational context for everything else we'll discuss. So, if you rewind the clock about 2 billion years, the Earth was a very different place. Life was entirely single-celled. You had these large archaea-like cells that were anaerobic, meaning they couldn't use oxygen. Actually, oxygen was toxic to them.
Yeah, the great oxygenation event was happening, and for these guys, it was basically an apocalypse.
Exactly. But then you had these smaller, really energetic bacteria, specifically alpha proteobacteria, that had figured out a trick. They could use oxygen to create energy.
Oh, interesting.
Yeah, and the theory, which was popularized by the brilliant Lynn Margulis, who was actually ridiculed for years before being vindicated, by the way, is that one of those large oxygen-hating cells engulfed the smaller bacterium.
So it basically tried to eat it, a hostile takeover.
Or a failed lunch, precisely, a failed lunch. But instead of digesting it, something incredible happened. They didn't kill each other. They formed a partnership.
A symbiosis.
Right. The big cell provided protection and nutrients, a safe harbor. And the little bacterium, which was essentially a high-performance engine, provided a massive amount of energy by processing that toxic oxygen.
And this is the exact moment life as we know it became possible. Because before this merger, life was slow. It was highly inefficient.
Oh, very.
Without that high-octane energy from the bacteria, you can't build complex organisms. You can't build a fern, let alone a human brain.
Correct. That little bacterium eventually evolved into what we now know as the mitochondrion.
Yeah.
But, and this is the crucial part that relates to our health today, it never fully stopped being a bacterium.
And that explains so much about why they're so weird, right?
Yeah.
I mean, structurally, they still look like bacteria. They have these double membranes.
And crucially, they have their own DNA. That is the smoking gun here.
Wow.
Yeah, your nucleus has the blueprints for you, your hair color, your height, your personality traits. That's your nuclear DNA, half from mom, half from dad.
Right.
But the mitochondria have their own separate ring of DNA called mtDNA. It's a completely separate operating system running inside your cells.
I was reading in the notes that this mtDNA is circular, just like bacterial DNA, whereas our nuclear DNA is linear. It really is an alien visitor that just never left.
It really is.
Yeah.
And because it's separate, it replicates independently. You can have hundreds or even thousands of mitochondria in a single cell, all dividing on their own schedule.
I like the analogy of a city here. If the cell is a sprawling metropolis, the nucleus is City Hall.
Okay.
It makes the laws, it holds the master plans, it directs the traffic. But the mitochondria are these independent power plants scattered all over the city.
That's a great way to put it.
They were once outside contractors, but now they're plugged into the grid.
That is a perfect way to visualize it. And just like a city, if the power plants start failing, it doesn't really matter how good the laws are at City Hall. The lights go out,
The subways stop.
the sanitation systems fail. Nothing works. But we actually have to update that analogy slightly based on the new science we have in front of us.
How so? Because the power plant analogy is the one we all lean on.
Well, we used to think they just churned out electricity, ATP, and that was it. But we now know they're deeply involved in governance too. They aren't just the utility company, they sit on the city council.
Oh, wow. What else are they doing?
They regulate calcium homeostasis, which is essentially the communication network of the cell. They synthesize steroids and hormones. And perhaps most importantly, they control apoptosis.
Apoptosis, that's programmed cell death, right? The suicide pact.
Correct. It is the self-destruct button. If a cell becomes too damaged or cancerous or infected, it is the mitochondria that pull the trigger to shut it down for the greater good of the organism.
So they make the call.
Yeah, they release specific proteins like cytochrome C that tell the cell it's time to shut down. So they aren't just making power, they are deciding who lives and who dies.
That creates a really high-stakes situation. If your power plant is also the guy holding the nuclear launch codes for self-destruction, you want that guy to be stable. You don't want him acting erratic or getting confused.
Precisely. And this brings us to the mechanics of how they actually work and where it goes wrong. Because to understand why we get tired or why we age, we have to look at the machinery itself. The process is called oxidative phosphorylation, or RxPHOS.
Okay, let's unpack this without getting too bogged down in the chemistry, but we do need to understand the battery concept because it comes up again and again in the research regarding supplements and toxins.
Right. So imagine an assembly line inside the inner membrane of the mitochondria. This is the electron transport chain. You eat food, carbs, fats, proteins, and your body breaks it down, and electrons are stripped from that food.
And these electrons are high-energy particles.
Exactly. They're passed down this assembly line through a series of massive protein complexes, complex 1, 2, 3, and 4.
And as they get passed along, they're doing work. It's like a bucket brigade.
That's it. As the electrons move, they pump protons, which are hydrogen ions, across the membrane. They're pumping them from the inside to the outside. This creates a massive buildup of pressure.
Like filling a dam, you're building up a positive charge on one side.
Yes, exactly like a hydroelectric dam. You have all this water, or protons, holding back massive potential energy. And then there is only one gate open, a turbine called ATP synthase.
Oh,
All those protons rush back through this turbine, causing it to physically spin.
it is literally a mechanical motor made of protein. I've seen animations of this. It spins at thousands of RPMs.
It is biological engineering at its absolute finest. That spinning motion smashes molecules together to create ATP, the energy currency of life. Every thought you have, every muscle twitch, every beat of your heart is powered by that turbine spinning.
But here's the catch, and this is where the danger comes in. This process involves high-energy electrons and oxygen. It is volatile. It's like having a fireplace in your living room.
I like that.
It provides heat, it's essential, but it also throws out sparks. In biology, we call those sparks reactive oxygen species, or ROS.
That is the perfect analogy. And normally the cell has fire screens and extinguishers, our internal antioxidant systems, to catch those sparks. But sometimes the sparks escape. They hit the furniture, they hit the walls.
And this is where the vulnerability comes in, because where is that mitochondrial DNA located?
Right next to the fireplace. Unlike the DNA in your nucleus, which is locked away in a vault and wrapped in protective proteins called histones, mitochondrial DNA is totally exposed.
It's just sitting right there.
Yeah, it's physically attached to the inner membrane right next to the electron transport chain where these ROS sparks are flying. It has very limited repair mechanisms compared to the nucleus. So you have the blueprints for the fireplace sitting right inside the fireplace.
That seems like a design flaw, or at least a very risky architectural decision.
It's a trade-off for efficiency. The genes need to be there to respond quickly to energy demands. But it means that over a lifetime, that DNA gets damaged.
And then what happens?
Well, when the blueprint gets damaged, the power plant starts building defective parts. Complex one gets a little wonky, it starts leaking more sparks, more ROS, which causes more damage. It is a vicious cycle.
And mitochondria aren't static, right? They don't just sit there taking the abuse. The research talks about mitochondrial dynamics, fission and fusion. This sounded like a dance to me.
It is a dance, and a really critical one. They are constantly shape-shifting. They fuse together to share resources. Imagine two power plants linking up their grids to stabilize the voltage. That's fusion.
So they cover for each other's weaknesses.
Exactly. If one mitochondrion has a damaged membrane but good DNA, and another has bad DNA but a good membrane, they fuse, mix contents, and complement each other. It's a survival strategy.
And then the opposite is fission.
Right. If a part of the mitochondria is hopelessly damaged, the network splits, that's fission, to isolate the bad part. It quarantines the damage.
And then comes the cleanup crew, mitophagy. This seems to be the buzzword in the longevity space right now.
Oh, everywhere. Mitophagy is quality control. The cell identifies those quarantined, broken, sputtering mitochondria and sends them to the recycling plant, the lysosome. The problem with aging and the diseases we are discussing is that this recycling system gets overwhelmed or sluggish.
So the trash just piles up.
Exactly. You end up with a cell full of bloated, dysfunctional mitochondria that aren't making enough energy and are leaking toxic free radicals. They take up space, they cause inflammation, and they don't do their job. That is the cellular definition of feeling old.
And this isn't just happening in a vacuum. It's not just inevitable entropy. This brings us to the second part of our discussion, the environmental and lifestyle assault. Because it seems like the modern world is specifically designed to jam up this machinery.
It is a perfect storm. We have a concept in the literature called mitotoxins. These are environmental exposures that specifically target and disable mitochondria. And when you dig into the list, it's disturbing how common some of these are.
What are the big offenders here? I know we saw heavy metals on the list.
Heavy metals are a major one. Lead, mercury, arsenic. The insidious thing is how they work. They mimic essential minerals. The mitochondrion has these specific transporters, basically doors, to let in things like calcium or iron because it needs them for the machinery. But lead, for example, is a shapeshifter. It tricks the transporter, gets inside, and then jams the gears of the enzymes.
It's like putting the wrong key in a lock and breaking it off. Or putting diesel in a gas engine.
It's worse. Once inside, they bind to the sulfur groups in the enzymes of the electron transport chain. They physically stop the electrons from moving, so your battery just stops charging.
And it's not just heavy metals. Pesticides are huge in the sources. There was a specific mention of a pesticide called rotenone. The notes said we use it in the lab to give animals Parkinson's disease. That stopped me in my tracks.
Yeah, it is a standard model for research. If a scientist wants to test a drug for Parkinson's, they take a healthy rat and infuse it with rotenone.
Why? What does it do?
Because rotenone is an incredible potent inhibitor of complex 1 in the mitochondria. It shuts down the first step of energy production.
And why does that cause Parkinson's specifically?
Because the neurons that produce dopamine, the ones that die in Parkinson's, are incredibly energy hungry. They have massive metabolic demands. So if you hit their mitochondria with rotenone, those neurons are the first to die.
Wow.
It shows us a direct causal link between mitochondrial poison and neurodegeneration. And yet, rotenone is a naturally occurring compound used in organic farming for years, though its use is more restricted now. But the class of chemicals, pesticides, often target mitochondrial respiration in insects. The problem is, we have mitochondria too.
That is terrifying. It really highlights that we aren't separate from our environment. And then there's the air we breathe. We talked about PM 2.5, particulate matter from pollution.
The evidence there is strong and growing. We used to think air pollution just irritated the lungs. But these PM 2.5 particles are so small, they cross the alveolar barrier into the bloodstream. They travel through the body. The research shows they damage the mitochondria in the endothelial cells, the lining of your blood vessels.
So the pollution is literally attacking the lining of your arteries.
Correct. When the mitochondria and the vessel walls fail, you get endothelial dysfunction. The vessels can't relax. Plaque builds up. This leads to atherosclerosis and heart disease. So air pollution isn't just a respiratory hazard. It's a mitochondrial hazard that drives heart attacks.
Now let's talk about something we have a bit more control over, diet. The sources mention a metabolic jam. I love that image because it feels like how I feel after a big pasta dinner.
It's the flooded engine analogy. Or think of the subway at rush hour. If you constantly flood your system with high glycemic foods, sugars, processed carbs, you are breaking down glucose rapidly. This floods the system with electron carriers, NADH. You are forcing way too much fuel into the electron transport chain.
So the assembly line is moving, but you're dumping boxes on it faster than the workers can pack them.
Exactly. The electrons start backing up. And when they back up, they stay on the complexes too long. This creates a state where they are much more likely to slip off and react with oxygen prematurely.
Creating those sparks, those free radicals we talked about.
Yes. The traffic jam causes a massive spike in oxidative stress. This is why type 2 diabetes is now being looked at as a mitochondrial disease.
Really?
Yeah, the mitochondria in the muscle cells are so overwhelmed by the constant influx of fuel that they basically shut the doors. They downregulate the insulin receptors to stop the flow. That is insulin resistance. It's a protective mechanism against mitochondrial burnout.
That reframes diabetes completely. It's not just high blood sugar. It's the cell screaming, "Stop feeding me!"
Right.
There was also a mention of seed oils in the research, specifically excess omega-6 fatty acids like linoleic acid. This is a controversial topic, but the mechanism seems specific to the membrane.
Yes, this is an area of active and intense investigation. The inner membrane of the mitochondrion contains a very special fat called cardiolipin. It's unique. It's not found really anywhere else in the body. It acts like the glue or the scaffolding holding the heavy machinery of the electron transport chain together.
So it keeps the complexes organized.
Right. Now, cardiolipin needs a specific structure to be sturdy. Some research suggests that when we consume a massive excess of omega-6s, which are prone to oxidation, these fatty acids get incorporated into the cardiolipin. Because they oxidize easily, the cardiolipin becomes unstable.
It's like building your scaffolding out of rusty metal.
Exactly. The complexes drift apart, the supercomplexes break down, efficiency drops, and again, you get more electron leaks. It creates a leaky membrane where you can't build that proton gradient effectively. You can't charge the battery because the casing is cracked.
So you're eating, you're breathing, you're existing in the modern world, and your mitochondria are taking hits from every angle. And the consequence isn't just that you need a nap, it's systemic failure.
Systemic energy failure. You have to remember the hierarchy of energy needs. The brain is 2% of your body weight, but takes 20% of your energy. If mitochondria falter, the brain is the first to feel it. Brain fog, memory loss, neurodegeneration.
And the heart too, obviously.
The heart never stops beating. It needs massive, constant energy. If mitochondria fail there, the pump weakens, heart failure. It connects everything.
This leads us right into the active debate. Because if oxidative stress and free radicals are the problem, if the sparks are burning down the house, shouldn't the solution be simple? Just take a bunch of antioxidants. Vitamin C, vitamin E. I mean, that's what the health food store has been telling us for decades.
You would think so. And for 50 years, that was the dogma. It was called the free radical theory of aging, proposed by Denham Harman in the 1950s. The idea was simple. Free radicals rust the body, antioxidants prevent rust, ergo antioxidants cure aging.
It's a clean, logical equation, but
Biology is rarely clean. The clinical trials didn't work. In fact, they were disastrous in some cases. Large meta-analyses show that taking high-dose antioxidant supplements like vitamin E or beta-carotene didn't extend life. In some studies, they actually increased mortality.
and specifically for exercise, taking high-dose vitamin C and E blocked the beneficial effects of training. That seems completely backward. Why would taking a healthy vitamin block the benefits of exercise?
Because of a concept that is absolutely central to modern understanding, mitohormesis.
Hormesis, that's the what doesn't kill you makes you stronger concept.
Exactly. It turns out the cell needs a little bit of stress. When you exercise, your mitochondria work hard. They produce a pulse of reactive oxygen species. For a long time, we thought that was just a bad side effect. But we now know that pulse of ROS is a signal. It's a bell ringing.
A bell that tells the nucleus what?
It tells the nucleus, hey, we are under heavy load here. We are struggling. Send reinforcements. The nucleus receives that ROS signal and activates defense genes. It produces endogenous antioxidants, the body's own powerful defense system. It triggers the production of more mitochondria.
So the free radicals are the messenger. And if you take a massive dose of vitamin C right after a workout,
You shoot the messenger. You wipe out the signal before it reaches the nucleus. The body thinks, oh, easy workout, no stress here, and it doesn't adapt. You don't get fitter. You don't get stronger.
that is a huge nuance.
Yeah.
It means timing and dosage are everything. We need balance, not a total wipeout of free radicals.
Exactly. We need to maintain redox signaling. It's a Goldilocks zone. Too much ROS is damage. Too little means no adaptation.
Here is another debate that stood out to me in the sources, and it feels like a chicken and egg problem. Do the mutations in mitochondrial DNA cause us to age, or do they happen because we are aging?
This is a fierce debate among gerontologists. To test this, scientists created a very special, very tragic mouse, the POLG mouse, P-O-L-G. This mouse was genetically engineered to have a defective DNA polymerase, the copier machine for mitochondrial DNA.
So every time it tried to replicate its mitochondrial DNA, it made typos.
Massive amounts of typos. Its mitochondria accumulated mutations at a rate hundreds of times faster than normal.
And what happened to the mouse? Did it just get sick?
It aged incredibly fast. By middle age, when a normal mouse would be vibrant, these mice were gray, balding, hunchbacked. They had osteoporosis, heart disease, anemia. They looked like tiny geriatric mice.
That seems like pretty definitive proof. If you break the DNA, you get aging.
It proved that mitochondrial mutations can drive aging. That was a huge finding. And here's the debate. When we look at normal aging in humans or wild mice, the mutation load usually doesn't get anywhere near as high as it did in the PLG mouse.
So in the real world, we might not be accumulating enough damage to explain why we get wrinkles and heart disease?
Exactly. The skeptics argue that while mutations are bad, they aren't the primary driver of normal aging. The counter-argument is the threshold effect. You can tolerate a certain amount of junk DNA in your mitochondria, maybe 60, 70, or 80%. The cell can compensate.
Right.
But once you cross that invisible line, the system collapses catastrophically. The debate is about how close normal humans get to that cliff edge.
Fascinating. So we might be walking around with 50% broken mitochondria and feel fine until we hit 51% and just crash. One more debate item, the niacin paradox. Niacin is vitamin B3. We know B3 is good for energy. It's a precursor to NAD+. But some studies showed high doses didn't help heart health and might even be bad.
This is a very recent finding, published just this year, and it really shook things up. We've been fortifying flour with niacin for decades, but researchers found that when the body processes excess niacin, it produces a terminal metabolite called 4-PY.
4-PY.
This 4-PY compound seems to be nasty. It triggers vascular inflammation. It upregulates the adhesion molecules and blood vessels that catch plaque.
So just blasting the system with generic B3 might backfire because you're creating this toxic byproduct.
It implies we need to be more sophisticated.
Yeah.
We can't just throw raw materials at the problem. We need to look at specific precursors that might bypass those toxic pathways or be utilized more efficiently.
Which is the perfect transition to the frontiers. What might change everything? If we can't just take vitamin E or generic B3, what can we do? Everyone is talking about NAD+. It's the buzzword of the decade in longevity.
For good reason. NAD+, nicotinamide adenine dinucleotide, is the gas in the tank. We talked about the electron transport chain. Well, NAD+ is the molecule that carries the electrons to the start of the chain. Without it, the assembly line stops immediately.
Right.
But it has a second job. It is the fuel for sirtuins.
Sirtuins, those are the longevity genes, right? The ones that David Sinclair talks about.
Yes, sirtuins are enzymes that repair DNA, regulate inflammation, and control stress resistance. But they're NAD dependent. They literally consume NAD+ to work. If you have no NAD+, your repair crew goes on strike.
And naturally, as we get older,
NAD+ levels crash. By the time you are middle-aged, you might have half the NAD+ you had in your 20s. That's a double whammy. You have more damage to repair, but less fuel to run the repair crew.
So the race is on to refill the tank. We have NR, nicotinamide riboside, and NMN, nicotinamide mononucleotide. These are supplements available right now. What is the difference, and what does the new science say?
They're both precursors, stepping stones the body uses to build NAD+. For a long time, there was a biological argument that NMN was too big to get into cells directly. The skeptics said, it has a phosphate group, it can't cross the membrane. It has to be broken down into NR first.
So taking NMN would be a waste because your body just turns it into NR anyway.
That was the argument. But recently, a specific transporter was discovered, SLC12A8.
SLC12A8 sounds like a personalized license plate.
It does, but it's a dedicated doorway in the gut lining specifically for NMN. This was a game changer because it suggests the body has a specific mechanism to uptake this molecule intact. Dr. Shinichiro Imai, a leader in this field, calls NMN a systemic signaling molecule. His NAD world theory suggests that tissues send NMN to each other in vesicles to coordinate aging.
So it's not just food, it's a message. Hey, keep the energy up.
Correct. He keeps the brain talking to the fat tissue, talking to the liver. When NAD drops, the conversation stops and things fall apart.
Now let's get a little more sci-fi. Mitochondrial transplantation. Are we really talking about taking mitochondria from one person and putting them into another? Like a kidney transplant, but microscopic?
We are. It is cutting edge, but the early data is wild. Imagine a massive heart attack. The heart muscle is starved of oxygen, the mitochondria swell and burst. The tissue is dying. Researchers have tried isolating healthy mitochondria from a donor or from the patient's own healthy skeletal muscle and injecting them directly into the damaged heart tissue.
And do they work? Do the cells accept them? I would think the immune system would attack them.
In animal models and some early human pediatric cases, yes, they work. The cells take up the new mitochondria through a process called macropinocytosis. They basically drink them up. The new mitochondria plug into the grid and energy production restarts. It rescues the tissue. It's like a jump start for the heart.
That is incredible. It changes the idea of permanent damage. What about peptides? I keep hearing about SS31.
SS31, or elemipretide, is fascinating because it works differently than anything else. It doesn't just float around. It targets that cardiolipin we talked about, the glue in the membrane. It is a tiny peptide that penetrates the mitochondria, finds the cardiolipin, and physically binds to it.
It's like putting a splint on a broken leg.
Exactly. It stabilizes the membrane structure. It helps the electron transport chain stand up straight and do its job, even in older cells. It improves efficiency without messing with the ROS signaling too much. It's structural reinforcement.
And finally, red light therapy. Photobiomodulation. This one always sounded like magic to me. You shine a red light on your skin and you get more energy. But there is a hard physics mechanism here, right?
It sounds like magic, but it's quantum biology. There's a specific enzyme in the electron transport chain, complex 4, or cytochrome C oxidase. This enzyme contains copper centers that absorb light at specific red and near-infrared wavelengths, around 660 to 850 nanometers.
So the enzyme acts like a solar panel.
In a way, yes. When it absorbs that photon of light, electrons are excited. It displaces nitric oxide, which can clog up the system, and allows oxygen to bind more freely. It literally pumps protons faster. You're using photon energy to charge the chemical battery.
So you are basically photosynthesis adjacent. We aren't plants, but we can use light to drive metabolism.
Precisely. And the effects are systemic. You treat the back, and you see benefits in the brain, likely because of signaling molecules released into the blood.
So what does this all mean? We have this incredible machinery, we are damaging it with our lifestyle, but we are learning how to fix it. But when we zoom out, the implications are massive. First off, looking at aging as a disease.
This is a major paradigm shift. The World Health Organization's ICD-11 classification has opened the door to treating aging-related decline as a condition. If mitochondria are the root cause, then fixing them isn't just about wellness or biohacking for tech bros, it's medicine.
And the economic impact.
It's in the billions, maybe trillions. If we can delay the onset of frailty, sarcopenia, which is muscle loss, dementia, heart failure, by just 5 years, by keeping mitochondria healthy, the burden on healthcare systems drops dramatically. The sick span shortens.
There is another huge implication here connecting to current events. Inflammaging and long COVID. This part of the research really connected the dots for me.
This is where the bacterial origin story comes back to haunt us. Remember we said mitochondria look like bacteria?
Right. They have that circular DNA.
Well, your immune system is trained to hunt bacteria. That is its primordial job. Yeah. If your mitochondria get damaged, say, by a virus or toxins, and they burst open, they release that mtDNA into the cytosol, the main fluid of the cell, or even into the bloodstream.
And the immune system sees it?
And it screams invasion. It recognizes the circular DNA and thinks you have a massive bacterial infection. It launches a full-scale inflammatory attack. It activates the CGA-serine pathway, pumping out cytokines. But there is no bacteria. It's just your own broken parts.
This is sterile inflammation. You are inflamed, you feel sick, you are tired, but there is no germ.
This is a leading theory for inflammaging, the chronic, low-grade inflammation of aging. And it is heavily implicated in ME/CFS, chronic fatigue syndrome, fibromyalgia, and long COVID. The theory is that the batteries are broken, they're spilling their contents, and the body is stuck in a permanent flu-like immune response fighting a ghost.
That is heartbreaking, but also hopeful because it gives us a target. If we can clean up the mitochondria, induce mitophagy to eat that trash, maybe we can stop the inflammation. But we have to address the elephant in the room, inequality.
Yes. For NAD+, peptide therapies, genetic testing for mitochondrial polymorphisms, mitochondrial transplants, these are expensive interventions.
Are we heading toward a world where the wealthy have high-performance cells and everyone else is running on empty, poisoned by the cheaper food and environmental toxins?
It is a genuine and worrying risk. Mitochondrial health could become the ultimate luxury good. We need to ensure that as these basic science discoveries translate to clinics, they are accessible. We can't just have longevity for the 1%.
Well, to that end, let's bring it down to the ground level. Not everyone can afford a mitochondrial transplant or peptide injections. What are the practical takeaways from the sources that anyone can apply today to protect their grid?
The good news is that the most powerful intervention is free: exercise. But not just any exercise. The sources are specific.
They pointed to HIIT, high-intensity interval training. Why is that better than a nice long jog for this specific purpose?
It goes back to the signal. You need to rapidly deplete your ATP reserves to shock the system. When ATP drops fast, the ratio of ATP to AMP changes. This triggers a sensor called AMPK.
AMPK is the fuel gauge.
Yes, and when the gauge hits empty, AMPK screams, "We are out of power. Build more plants." This triggers PGC1-alpha, the master regulator of mitochondrial biogenesis. It tells the DNA to print more mitochondria.
So you have to sprint. You have to get breathless. You have to make the cell panic just for a moment.
You need that intensity to force the adaptation. Zone 2 cardio, low intensity, is great for efficiency. It greases the gears. But for building new mitochondria, intensity is key.
What about supplements? We mentioned a few, but if someone wanted to support their mitochondria, what is the evidence-based shortlist?
CoQ10 is the classic. It is a vital electron carrier in the chain, moving electrons from complex 1 and 2 to complex 3. If you are low on it, and statins can lower it, by the way, the assembly line stops. But absorption is tricky. Forms like ubiquinol are better absorbed, and there are targeted versions like MitoQ designed to penetrate the mitochondrial membrane specifically.
And PQQ.
PQQ is interesting because it stimulates biogenesis. It helps grow new mitochondria, not just support the old ones. It seems to work synergistically with CoQ10. And of course, the NAD plus boosters we discussed, NMN or NR, to keep the fuel tank full as you age.
And finally, sleep. We always say get more sleep, but specifically for mitochondria.
Sleep is when the glymphatic system activates. It's a plumbing system in the brain that opens up at night to wash away metabolic waste products. If you don't sleep, that trash accumulates around the mitochondria and suffocates them. Plus, mitochondrial dynamics, the fission and fusion dance, follows a circadian rhythm. Disrupted sleep creates chaotic, fragmented mitochondria.
So protect the rhythm.
Protect the rhythm. Eat within a window to give your mitochondria a break. Get sunlight to set the clock. It sounds basic, but it's the foundation that makes the fancy peptides work.
It's amazing how it all circles back to the basics, but now we know the why. We aren't just resting, we are running a complex recycling and repair program.
Exactly. Knowledge is the first step to taking control of the controls. And there's still so much left for you to explore on your own with this. Like, how does extreme cold exposure tie into mitochondrial uncoupling? It's a whole other rabbit hole.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support.
And to our listeners, thank you for being part of this journey with us. We hope you enjoyed today's discussion. If you did, be sure to subscribe and support us on Patreon. And of course, you can write to us in comments if a specific topic needed to be covered, which help us all to grow.
Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.